Hello again. So moving on again, a lot of these explanations of some of the terms like neomorphs. Here it gives you the example: gain of function mutations such as Drosophila antennapedia. If some textbooks will show you Drosophila that has legs on the head, so this is antennapedia. It causes legs to sprout from the segment where antennae should develop, and this is called neomorphic. So because it's something that is new, although it may not have any function. Now look at this little sentence again. So up here it says alleles with the same activity are called isoalleles. Mutations which do cause a change in phenotype, right? Do change in the phenotype, may still be neutral if the different phenotype does not affect fitness. So again, you're talking about function-wise or overall fitness. Effect of mutation can be considered at several levels: the effect of nucleotide sequence, so whether what type of mutation, the effects on activity, the effects on phenotype, and then finally the effect of overall fitness. So this is how you can probably classify mutations. Okay. All right. The following sections, especially 15.3 and so on, I will not say that I give that much attention to it, but it'll be nice for you to have a look at it. So it talks about the nature of mutation, and most of this is a topic where you talk about evolution, you talk about population. So never mind. So it says here the spectrum and distribution of mutations in populations on genomes is non-random due to the existence of mutation hotspots. In the genome, some places are more prone to undergo mutations than others. And then, for example, tandemly repetitive DNA are prone to slip strand replication and unequal exchange. Inverted repeats. You have tandem repeats, you have inverted repeats. Inverted repeats are hotspots for inversion. If you have a 5-methylcytosine due to methylation, the 5-methylcytosines are hotspots for C to T transitions. One of the things that you should notice, again, if you are looking at the molecular basis of mutations in your second year, you will find that a lot of the mutations, the alkylation, the changes the property of the bases and so on. A lot of the mutations result in transitions. Why is this important? If you look at the nature of nucleotides, you will find, you'll see this. This statement: each base has 2 choices for transversion and only 1 for transition. If you remember, it's if I can show you in this picture, right? Okay, let me try and see if I can change this for a bit. Right. Okay, if you remember, if you have A, I'll just give it a T, I give it a G, a C, right? What is transition? Transition is between pyrimidine to purine to purine. So transition is this. This is transition: T to C, C to T, A to G, G to A. Transition. Whereas transversion is T to G, G to T, or A to C. Alright. Also, G can change into a C, C can change into a G, A can change into a T, T can change into a... Correct? So how many transitions and how many transversions. So in this, you'll have 4 transitions, and then you will have a total of 8 transversions. And this also, you know, the statement says, where is it? Each base has 2 choices for transversion and only 1 for transition. Each base, let's say we look at A, have 2 changes for, have 2 options for transition, right? Sorry, sorry. let me do that again. Each base has 2 choices for transversion and 1 choice for transition, right? So here it is. So this base A has 2 choices for transversion. That means it can change into a T, it can change into a C, transversion, but it only has 1 choice for transition A to G. All right. Now, if you have 4 transitions and 8 transversions, so in the genome, you would expect to see more transversions. But as it is, in fact, the opposite is true. It says here, transitions are twice as common as transversions. Why? Because a lot of mutations actually cause transitions rather than transversions. Okay, so this is what it's talking about. Okay, I'll see you in the next slide.